All right, folks, we're talking about the fundamental theorem of similarity today. So I have a couple of examples we'll go through here regarding that, and we'll clear up what that means. So the fundamental theorem of similarity is the theme of the day. And one thing to note about similarity is this little symbol here, this little squiggly thing. This means similar. And similar figures are figures that are the same shape, they're just different sizes, and they're related proportionally. So we're going to investigate more what that means, and I say proportionally here in just a second, because we have these two triangles, A, B, and C, then A prime, B prime, and C prime. They are similar because we're told that they're similar. We're given the side lengths of triangle ABC, 3, 4, and 5, and then we're given a K, which is the magnitude or the scale factor or the ratio of similitude. It goes by many different names, and that is in this instance 3, and we have to fill in the missing sides. So one thing to note as far as similarity goes is that if two figures are similar, their angle measures stay the same. So you'll notice we have this right angle right here at B prime. It's still a right angle, so nothing has changed. As a result, angle C will be equivalent to C prime, and angle A will be equivalent to A prime. So angles don't change if figures are similar. The side lengths, however, do. As you can see, these are two totally different side lengths of triangles, and we can find those measures with the scale factor, or the K, or the magnitude, or the ratio of similitude. Again, goes by many things. In this case, it's 3. So all we're going to do here is take each of these side lengths, multiply it by the ratio of similitude, and we'll get the corresponding side length. So filling in the missing sides, we can say that A prime to B prime is going to be 9 because 3 times the scale factor 3 is 9. And AB corresponds to A prime, B prime. As a result, B prime, C prime is going to be 12 because 4 times 3 is 12. And then A prime to C prime is going to be 15 because 5 times 3 is 15. So the perimeter we can look at now to kind of get at this idea of the fundamental theorem of similarity. The perimeter of ABC right here is going to be 12 because 5 plus 3 plus 4 is 12. The perimeter of A prime, B prime, C prime is 36 because 9 plus 12 plus 15 is 36. And then we can investigate this a little bit further and talk about the areas of the triangles. So the area of triangle ABC is going to be 6 because 3 times 4, the length times the height is 12 divided by 2, formula for the area of a triangle. So the area of ABC is 6. The area of A prime, B prime, C prime is 54 because 12 times 9 divided by 2 is 54. So we have the relationships between the areas, relationships between the perimeters, and then the relationships between the areas here. And there is a relationship there that exists with respect to the magnitude, which we're going to talk about right now. So let's say we have two figures that are similar, as we did in the last example, and K is the ratio of similitude, or the magnitude, or the scale factor, whatever you want to call it. Then these things are true, and we can take a look at that with respect to what we just did. First of all, number one, the perimeter of one of the figures times K is the perimeter of the resulting figure, of the similar figure. The areas, however, are related also by that ratio of similitude, but it's by the scale factor squared. And we'll go back and take a look at that in just a minute to kind of connect that to what we just did. And then the volumes are going to be related by the scale factor or the ratio of similitude to the third power. This one we haven't looked at just yet, but we can take a look at the perimeter and area. Going back here real quick, is that we'll notice that 12 times 3 is 36 because the perimeters are related by the scale factor. The areas are related by the scale factor squared. You'll notice that 6 times 3, the scale factor, is not 54, but the scale factor squared is 9. 9 times 6 is 54. So that's what this fundamental theorem of similarity is getting at here. So that the perimeters, the actual lengths or the distances, are related by the scale factor. The areas are related by the scale factor squared. And then the volumes will be related by the scale factor to the third power. So a couple instances there that we need to make note of, which is the fundamental theorem of similarity. So another example, suppose that we have two figures that are similar and their lengths are in the ratio of 7 to 1. So the ratio of similitude, scale factor, the K, whatever, is going to be 7 to 1 or 7. What is the ratios of their volumes? Well, 7 to 1 is the ratio that we have, which is kind of like the K to 1, which is our ratio of similitude. Our general ratio of similitude is K. We talk about volume. The volume is going to be the ratio to the third power. And 7 to the third power is 343. So if two figures are similar with their lengths of a scale factor or ratio of similitude of 7 to 1, then those two figures' volumes are related by the ratio of similitude of 343 to 1, because 343 is 7 to the third power. Another instance here, more applicable type of problem here. Suppose that we have two triangular prisms that are similar with a ratio of similitude of 8/10. That's 0.8. If the larger prism has a volume of 250 centimeters cubed, what is the volume of the smaller triangular prism? So we have some information here. There are prisms for a picture there to kind of see what that looks like. And we know that the ratio of similitude is 0.8. So what that means is that if I take whatever length this is here and multiply it by 0.8, I get the lengths of the smaller triangular prism. And I know that because right here, we see that because the ratio of similitude is 0.8, and we can assume that that's just K. Our K is 0.8. The larger prism has a volume, this prism right here has a volume of 250. We want to find the volume of the smaller one. Well, we know that volume is related by the scale factor to the third power. So there's our volume of 250. We know that if we multiply this by K to the third power, right here, 0.8, we should get the volume of the smaller one. So we're going to do 250 times K to the third. Why K to the third? Because it's volume. 250 times K to the third is 250 times 0.8 to the third power. 0.8 to the third power, doing order of operations, and then multiplying that by 250 will give us 128, the 128 centimeters cubed, for the sake of getting the units on there. The 128 comes from multiplying the volume of the larger one by the scale factor to the third power, because if these side lengths are related by 0.8, then the volume of the figures is going to be related to each other by the scale factor to the third power. Why? Because that's what the fundamental theorem of similarity tells us. We'll get a value of 128. So it's important to note, what exactly are you given? Are you given lengths? Are you given areas? Or are you given volumes, and then determining what K is, or K to the third power, based on that information, and you can find the missing values.